So thanks for the kind words, for the kind introduction. Yeah, my pleasure to be back up here on the stage, this time with a dedicated session about what we tend to call the core resilience features. And I'll go into what that actually means and the what's and whys of what we're doing here in just a moment. Some of the motivation behind what we're doing here just is very indicative of the Spring portfolio overall. If you look at the wider Spring portfolio, you can see some projects appearing as independent projects being merged into other parts of the projects. We sometimes rearrange things within the Spring portfolio, and this is actually very related here. There used to be sort of a Spring retry project, quite a bit of which has been sort of revisited, redesigned, re-implemented as core features of the core programming model. But it's by no means the first time this is happening. But as you will have noticed, these things only happen as a new generation of the framework launches, right? So that's why it happens now in Spring Framework 7 and in former times. Even go far enough back in time, and you'll find out that even configuration classes, add configuration classes, used to be an extension called Spring Java Config, having been brought into the core Spring framework in Spring Framework 3.0. Now very core elements of the programming model used to be sort of extension projects external to the core framework, but got merged in over time. Yeah, with that said, that's exactly where we are here. We revisited an important, interesting space for the programming model itself. This is a little bit in the light of modern-day threading architecture, so I'll go into this in a moment. Things are not quite, the conditions that we live within here are not quite the same from 10 years ago. Anyway, so as usual, this is common annotations, part of the common annotation programming model. So just like you'll find at transactional, at cacheable, at async, you'll now find features such as at retryable and at concurrency limit. They operate at the very same level. They are part of the core programming model, hence core resilience features. None of this is implemented actually in an annotation-centric way, because of course, core retrying or even say core concurrency management is a very programmatic affair underneath the covers. And we made all those levels public, right? So you can programmatically interact with what we call a RetryTemplate, and you can interact with what we call task executors for similar purposes or even the very same purposes that you use the annotations for. It's your choice. Annotations obviously complement existing annotated components very nicely, whereas if you have existing programmatic arrangements, by all means consider the more flexible and to some degree more expressive programmatic variants. Now, before we primarily spend our time looking at source code variations, I'd like to discuss a couple of the design goals, because they aren't necessarily obvious. A key design goal here actually is virtual threads friendliness. So why that, and what does that even mean? Well, in traditional architectures, say a traditional platform thread management scenario, you have a thread pool, right? A thread pool with a limit. So thread pools, any kind of pooling arrangement is usually naturally limited, bound by an upper bound. If your thread pool does not allow for more than 10 threads in the pool, your effective concurrency level using that thread pool is never going to be higher than 10, right? So there's an implicit concurrency limit baked into pooling arrangements. The same is true for any pool that makes you block on waiting for like a connection to be obtained from it, like a JDBC connection pool. If it's configured to make clients block until the connection becomes available, It's a natural concurrency limit. If you have a JDBC connection pool of size 10 max, you're never going to hit the database with more than 10 connections in parallel, a natural concurrency limit. The other part of this, right, is that the introduction of reactive programming, quite a while ago, gave us primitives like basically building blocks, elements, operators for expressing your concurrent needs. So there's ways of crafting a very fine-tuned reactive pipeline, which naturally even has retry features baked in and can also naturally control the level of concurrency of that particular pipeline through how many things it spins off and joins again. So we are trying to be virtual threads friendly a little bit from that perspective. Consider what you can do with reactive programming right now, with Project Reactor in particular, all of the nuances and all of the operators that it provides. We're trying to port some of that experience, some of that flexibility and some of those building blocks over to virtual thread-based architectures, where you can use similarly fine-grained, nuanced ways of processing in a virtual thread-based blocking style, right? And of course, virtual threads increase the concurrency exposure, right? You can start a virtual thread at any point. It's always going to, well, start and add itself to a sort of queue, right? There's no natural limit to the number of virtual threads. That's part of the game, part of the design there. You can literally have 1 million virtual threads. They're all going to be attached to a very limited number of carrier threads underneath the cover. But the number of virtual threads themselves is basically unbound, unlimited. And you don't usually pool them, or at least not in the traditional sense. So there's no pool-imposed limit for virtual threads. If you want to constrain your actual concurrency level, right, the maximum processing hitting a particular service, a particular component, through in a virtual thread-based architectures, you need to do so through custom means, like adding some custom semaphores, adding our concurrency limiting features here. You need to do so explicitly, whereas in a traditional thread pool environment, it was basically implicitly coming from the thread pool setup. So things that used to be implicitly applying now have to be explicitly expressed in a virtual thread-based architecture. There's a bit of alignment also in the design goals here. Backoff is something we already have in the core framework. We use it for listener container management, for basically connection recovery purposes. So there's a very close relationship with what retries have to do if they have to back off and wait a little until you attempt the next retry. So we're trying to reuse that to the best possible degree in those core features, rather than reinventing anything similar. And for an inspiration, Project Reactor has a very flexible retry back-off spec arrangement that you can apply to reactive pipelines. This has been a source of inspiration for our retry features, for what you can, for how you can express yourself, and for basically what you can fine-tune. We were trying to align with everything Reactor can do there. All right. At the same time, whenever we design something new for the core programming model, we also need to know how far we intend to take this. What are we trying to cover, and where do we draw the line? Drawing the lines is hard, right? In particular, if you're talking about a programming model which theoretically could make many things first class in the core programming model, we chose to focus on basically the same level that reactive operators are at. Or you could say Java util concurrent level. So basically what the Java util concurrent primitives give you in the core JDK libraries, we operate at pretty much the same level, just in a more convenient fashion. So we won't do more than this. but we're trying to significantly improve the developer experience, of course. We're trying to empower architectures on virtual threads, but the Java util concurrency primitives are concurrent primitives are actually very virtual threads aligned already, so that goes along with it. An equally important, maybe even more important point. We're talking about the core programming model. This is the internals of a service that you're implementing. You're basically implementing repositories, services, delegates. You're implementing maybe specific controller endpoints, specific message gateways, right? We're talking about a pretty fine-grained component level that you are applying these features to. This is not meant to replace or even tackle the same problems that, say, circuit breakers, rate limiters, cloud platform level features of that kind. Those remain separate. Those are applied to your deployment, to the cloud platform handling your deployments, to the platform auto-scaling your deployment. There are measures at place at that level, and I would highly recommend to use those, to keep using those, right? What we provide here are additional measures within the system for specific components to be a little more fine-grained of which component needs what kind of a measure applied. And just like security, right? Or security measures that you apply to your system, to your implementation, it's a multi-level affair. It's a good idea to do that with security, right? Do it at the entry point, have some level of security management within the application as well when you're hitting critical services. The same is true here. Try to manage basically the boundary level, the system level, platform level rate limiting. Try to define how much you want to be forwarded to your service there. Whereas within the service, you might be delegating to other services. You might be using some internal components where you know that they, again, produce target messages, talk to some target database, and you want to constrain those. Or you want retry management for those. Then now we're talking, right? That's what the core resilience features are for. Right. So much for a bit of design discussion. Now let me show you a couple of examples. Those are pretty straightforward. Anyone knowing Spring Retry, the former Spring Retry project, which has been around for many years, should find themselves familiar here. But this is basically common ground in terms of usage. So you'll find, say, Resilience for J or other projects out there, other programming models out there use very similar annotations in particular here. In our case, we have a core retriable annotation with many attributes that you can customize. We'll go into some of them, but also sensible defaults. So if you just say @retriable, you'll get basically initial attempt plus a maximum of 3 retries. Delays per second. There's sensible defaults behind those. Now, the methods that you choose to apply those to are of your choice, obviously, right? What's worth retrying in case of failure? And in case of which specific failures is it worth retrying? You need to say so, right? We can't infer that. So you're going to be as specific as you can. Don't try to micromanage necessarily every definition here, but you can be as specific as you need to be. For a start, how often do you want to retry for a particular target system before you give up? Depends on factors that you know best. And say for a messaging system, you might have more retry attempts maybe than, say, for a database that is usually always available, where it's very unusual for it not to be reachable or for it to hit a timeout. So maybe for a messaging endpoint, as has been suggested here in this little code sketch, a notification passed on to a JMS destination, maybe you'll increase the maximum number of retries a little. If you want to be more specific, about which exceptions are worth retrying. You can be so, right? By default, we're basically retrying any failure. If the method throws an exception, unless you say otherwise, we're always going to retry it if you annotate it with @retryable. If you only want to, in this case, handle message delivery exceptions, so a very specific kind of exception that, in this case, would come out of the out of our messaging exception hierarchy. Say, let's take a database case. You're trying to store something through JPA or maybe through some custom JDBC usage, and you want to react to optimistic locking exceptions or generally locking failures. You can say so, right? You can react to optimistic locking exceptions or to our hierarchy of locking failure exceptions covering all kinds of locking scenarios, and you're only going to retry those, but not if anything out of the ordinary happens, right? So your choice, your method that you're annotating, you know what you want to retry. Obviously, there's more attributes waiting for you, and they can be combined. So if you want to retry message delivery exceptions, you only have includes, no excludes. So you can also exclude specific exceptions if that's easier for you, right? Retry everything other than this. There's an excludes attribute for this. A maximum number of retries. In this case, a shortened delay. So how long are you going to wait? How long are you going to back off before the next attempt, right? If an initial failure happened, or also between retry attempts. That's the delay. There's a maximum delay. So why is there a maximum delay as well down here? Because we have a multiplier factor in here. So which means first 100 milliseconds, on the second back off 200 milliseconds, next one, well, do the math, right? 400, 800. It would add up, but if you want to limit this, possibly also for customizable delays, where you always want to have a hard limit. So whatever the multiplication leads to, never wait longer than this between attempts, right? Then that's what max delay is for. We also have a jitter feature in here that's indicated here. Jittering is basically a little artificial deviation, right? Don't always make a strict 100 milliseconds. Go maybe 10 milliseconds below or above it for every attempt. So this classic jittering feature, as known from network retries, is also available here. It's literally, it uses the base calculation, the delay plus multipliers for every attempt. It uses that as the reference point, and then just jitters a little, so that if you have multiple service instances running into the same retry for the same method hitting the same target service, that they don't hit the target service at the very same time, so that there's a little deviation. So that's jittering. Whether you need to be as fine-grained as this, it's your decision, right? You can keep it simple. Just go with the defaults. No jitter, fixed delay. Now, a nuance that may not be so obvious, since I was saying we're trying to provide building blocks that match what reactive programming gives you, what Reactor gives you, they actually also interact directly. If you have a method with a reactive return type, just like our add_transactional or our add_cacheable, they are actually specifically understood. So just quickly, if you do transaction management or cache management, there's basically two modes of operation. We immediately detect whether the method is imperative or whether it returns a reactive pipeline, and there's a different mode of operation if there's a reactive return type. For transactional, we basically decorate the reactive pipeline with a transactional operator. Similar for caching, we decorate the pipeline to perform a cache lookup first and only then call the actual reactive pipeline. Different mode of operation. The same is true here. If there's a reactive pipeline return, the mono or flux in reactor terms, we actually decorate the reactive pipeline. We use the features provided by Reactor, the retry backoff spec feature in Reactor, and translate the retriable attributes, the definition that you attached as an annotation, we translate it onto the reactive pipeline, including the features that we have in customizable form, which isn't actually shown here, but you can, there's string equivalents of those attributes. You can pass in placeholders that come in from some configuration source. So the annotation is actually a little more flexible in being able to pull, say, the maximum number of retries or the delay and that stuff from external configuration sources through the common Spring placeholder model. And it's still being applied to the reactive pipeline that this method returns. So we won't go into this too deeply, but retryable is actually capable of handling reactive methods. Not least of it all, and this is only really a quick hint in an area that is still a little evolving, there are opportunities to monitor what's happening, well, we have the facilities in there to basically listen to what's happening. Every time that an retriable method fails, it publishes a method retry event, which is an extension of method failure event, which is something that you would, where it makes a general sense to have a listener for it and just log it specifically, because it's a little out of the ordinary for that to happen on methods that you declare so. And method retry event itself exposes some of the state, so you can basically reason about what failed, if it's already the final step that failed, or if it's an intermediate failure, and just log it accordingly. It's primarily meant for logging. You're not supposed to influence the retry algorithm itself. It's just tracking it, basically, listening to it. So there's an eventing model behind this, and we'll see. There's also a programmatic listener equivalent for the programmatic facilities in a bit. All right. So what is this add concurrency limit thing? The kind of second part of the current resilience features. Concurrency limiting is an old facility in Spring. Very literally, I mean, this has been in there since like 2004. So 22 years old. As an AOP interceptor and as a mechanism to constrain what we call the simple async task executor. We basically took this feature, or this way of expressing a concurrency limit, and made it an annotation-based feature. Add concurrency limit is basically applying an AOP interceptor to your method, right? It decorates your method with a proxy plus a what we call a concurrency throttle interceptor, and it's going to make sure that your method is not being hit by more than 10 threads in parallel with a concurrency limit of 10. There's some configuration options in, you can basically, usually, by default it's going to block if one more comes in, and the concurrency limit is already exceeded, would be exceeded, then you're basically blocking the caller until some other thread leaves the method, right? You can also make it fail early if you prefer, but the usual way is blocking. Why blocking? Well, that's exactly what you should be doing for a virtual thread that is currently not able to continue processing, right? You're supposed to block it. Again, virtual threads, friendliness. In a virtual thread scenario, blocking is a cheap operation and part of the idiomatic way of implementing a virtual thread-based processing sequence. So it's a little bit like you had a semaphore and a custom semaphore, and you basically saying, tell me what I'm allowed to enter. The concurrency limit itself is obviously customizable. You can also put a placeholder in there, so it's, you can externalize the actual configuration setting. Concurrency limiting of 1 essentially makes it a sort of lock. Right? It's almost like you had a Java util concurrent lock around it, and just waiting for the lock to be released. So it's a little bit like you had a synchronized method, basically, or a custom lock usage. So that would be a special case. But yeah, it's definitely possible to do this, right? You can basically use concurrency limit like a declarative lock if you want, right? At a pretty at a method, at a level of method granularity. So yeah, the concurrency limiting is basically, well, almost literally like using a Java util concurrent lock or a semaphore, right? Or like a synchronized keyword. It's a JVM local way of constraining how many threads are allowed to enter that method at the same time. In that sense, it has no technical relationship with any kind of rate limiting at the service entry point level or at the platform deployment level, right? It is sort of conceptually related in saying maybe you may have rate limited your service, but if the code path in your service, the code flow, leads to this method being invoked, you have a harder limit applying here, right? The service itself may be hit by whatever number of requests at the same time. This method, you only want to be hit by one thread at the same time, or 10 threads at the same time, or if there's a placeholder, by a configurable number of threads at the same time. It's as simple as this. It's also no more than this, right? Distributed lock management is an entirely different topic. In the Spring portfolio, this would be more like a Spring Cloud level feature. And that's where you find such features. That's where you find circuit breakers and rate limiting. At the platform level or at the boundary level, cloud frameworks, basically, right? Or in the Spring ecosystem, the facilities that Spring Cloud provides for such purposes. And just quick reminder, multi-level concurrency management, right? So it's a good idea to constrain things at the entry point, how many requests are allowed to hit the system, and if you have sensitive components inside, to also express limits at a more fine granular level like here. Right, one more thing. How can you actually activate all of this? In the typical Spring sense, at enable resilient methods, like at enable transaction management. You can customize the proxy options and that stuff as attributes, but by default, it's just this. It makes at retriable and at concurrency limit to actually automatically be wrapped with an interceptor, as you're used to from at enable transaction management. Now, let's move on to the programmatic APIs. Without going too deeply into every nuance of it, you'll find a similarity here in terms of capabilities, obviously, because at retriable underneath the covers either uses RetryTemplate or the reactor retry backoff spec. There's those two code paths, right, for non-reactive and reactive methods. So obviously they would have similar or the same capabilities, but there's a little more flexibility if you use those programmatic elements directly. So for a simple default usage, RetryTemplate is basically a callback-based way of expressing a retry. RetryTemplate is a very light instance. Feel free to reuse it if you want to reuse its configuration. Feel free to just create a new one for every operation. That's fine. It's very lightweight. RetryTemplate invoked takes a callback and applies the retry policy, in this case the default retry policy, to the callback. So it's going to invoke it once. If the initial attempt fails, it's going into the retry procedure, and it's going to do as many retries as allowed. It's going to do the backoff as defined, just like for the annotation-based case. If you want to customize it, feel free to pass in a retry policy. This is a builder. It's basically an interface, but it has a builder with it. So if you just want to customize the max retries, do it here at this level. If you want to be a little more fine-grained, there's literally a builder where, again, we constrain the retries to message delivery exceptions. There might be some custom excludes, maybe some sub-exceptions of message delivery exception. And everything else you've been seeing before is available here on retry policy. RetryTemplate takes a retry policy. It's basically the executor for a retry policy, if you want to see it like this, and then you invoke it again. Invoke semantics, we'll get to that a little later, are basically exceptions, original exceptions get propagated back to the caller. We'll get into this ultimate original exceptions, right? If we exhaust the retry policy, if we ultimately fail, we try to retry, but no luck, right? And there's a timeout that you can configure also for the overall entire retry procedure. So if you need that, but there might be an exception coming back to you, to the caller, eventually. And that exception in the invoke case is like with an annotated method, it's the original exception. So if the JMS client threw a message delivery exception, and yet another one, and yet another one, and yet another one, then we give up, you're going to get the last message delivery exception propagated to the caller. One more just to give you an illustration that everything is there. The retry policy has basically the same settings as at retriable. In this case, duration-based, so there's a little bit of a difference because it's programmatic. But yeah, feel free to build it as specific as you need it. Pass it into the retry template. Use the template to invoke some target operation. So yeah, now we come back to the exception handling nuances. If you want to handle this ultimate exception coming out of the retry template, try catchwork, right? Around the retry template invocation gives you exactly that. You can do the same to an at-retriable method. If you call the method, ultimately, policy exhausted, you get the last exception back. And the caller can actually try to catch it and try to handle it. The invocation here is basically without a return value, runnable-based. There's a variation with the supplier where it's including a return value, right? So you can then literally use it just like an at-retriable method. Might be a method might be some target operation without a return value, or it might be one that you need to carry through. And if you need to handle the ultimate exception coming out of it, there's the outer try catch block doing exactly that. So notice the little difference there. This is the invoke method on retry template, having invocation semantics, basically like a method invocation, in terms of exception propagation. There's an underlying, say, slightly more powerful method called execute. Takes the callback. However, what comes out of it is a retry exception. So if anything fails that is coming out of the retry procedure, you ultimately get a retry exception. What's the difference? Well, it's a checked exception, which is unusual in Spring APIs. But it's unusual to get that because you're not supposed to propagate it. You're supposed to reason about the state of the retry exception. In this case, you have full insight into the retry state, how many attempts we had, all the exceptions that occurred, or you can see the last exception if you want it, right? You can basically do some processing. Maybe you log right there if you have specific logging for this specific operation. And ultimately, you rethrow the last exception, or you throw a custom exception with this as a cause. That's your call. It's basically a combination of all the exceptions that happened with a little bit of retry state management around it, of being fully exposed to you as an outcome of the retry attempts. The alternative, sort of, kind of an alternative, right, is to specify a retry listener. So what's the idea here? In the traditional case, you basically let it all happen, and then you wait for the final state of affairs. You get the retry exception exposing all of the state of the outcome of the entire retry procedure, and then you act. The alternative is to keep using the invoke method down here, the one that propagates the last original exception, if it happened that way, and specifying a retry listener on the retry template allowing you to get a callback, and this is just one of the retry listener methods, but it's maybe the most useful or the most common one. You can get a callback for every retriable execution. So every time we have to, we failed, we can basically get a callback and see like, okay, let me log this, let me forward it to some monitoring as it happened, right? Then we may back off a couple of seconds in the meantime, according to your specification. You get the callback right when it happened, for everything that happens. And at the very end, the original exception gets propagated to the caller if we ultimately fail. So it's a different way of interacting with the retry state management. Now, last but not least, and maybe the least obvious part of all of this, concurrency limiting is not only available for annotations. As mentioned before, this actually is an old sort of idea, an old feature that is exposed in various places in Spring Framework delegates and Spring Framework execution facilities. In sort of recent terms, it is in particular available on sync task executor. So what is this? This is part of Spring's task executor abstraction. This is the same kind of thing that lets you choose between a simple async task executor or a thread pool task executor. It's all the Spring components being able to spawn some async operations. They all take a task executor. It's like a Java util concurrent executor with a little bit of definition around it. That's really what it is. Think Java util concurrent executor. Now, the sync task executor as of 7.0, that's actually new that it acquired that, is a delegate with concurrency limiting features baked in. So you can take a sync task executor, again, just created, it's a lightweight instance, specify a concurrency limit, then call execute on it around an operation of your choice, and it's going to constrain the threads being allowed to enter that operation at the same time, just like add concurrency limit does for method invocations. It's literally the equivalent feature for programmatic purposes, sort of the equivalent of RetryTemplate, right? If you see RetryTemplate as an equivalent of retriable, then this is the equivalent of concurrency limits. Why is this in sync task executor? Well, this makes it configurable in interesting ways, not least of it all for testing purposes. You can also reuse the task executor definition. You can create the instance in line, like here, but you could also define it as a bean, make it injectable, maybe for a customizable concurrency limit, right? You pass around a custom task executor instance that in one place in the configuration is configured with a specific concurrency limit. Everywhere else, you inject it with add auto-wide, whatever, and then just keep delegating to it. So there's flexibility in reusing a pre-configured instance. That's why there is a delegate for it and not just a utility. Now we have a variation here on sync task executor with a return value, which for a task executor is a little unusual because think executor abstraction, it's actually primarily meant for async tasks, and an async task is not going to give you a return value immediately, right? Only the sync task executor can produce a return value right away. So you've got an execute method of that kind here, and making it fully capable to do whatever add concurrency limit for a method invocation can do. And now this is actually an old feature, even if it looks, it is of very similar style, right? It looks very similar. The simple async task executor also has a set concurrency limit method, but a 22-year-old one. And this method here, this executor here, is actually going to create a new thread and pass basically this callback, the runnable, the callable, to the asynchronous thread. This is also an implementation of async task executor, so it actually has methods like submit, returning futures, or submit completable, returning a completable future. It has all the facilities of asynchronous task management that you would expect that are also available on the thread pool executors. you have them here as well, right? But stylistically, it's very similar. This is spawning asynchronous threads, right? So obviously, it's a bit differently purposed. Not least of it all, it's one of our primary hooks into virtual threads. So setting the virtual threads flag to true here makes the simple async task executor produce virtual threads for every callback, which also kind of provides a nice circle of the problem space here, right? So in case you want to spawn asynchronous tasks with virtual threads, rather than just being invoked within a virtual thread, you can do so here. You would usually configure the simple async task executor once as a bean, inject it, and just use it. Then it's pre-configured to use virtual threads, pre-configured to use a concurrency limit. And in this context, you basically have a sort of alternative to a traditional thread pool, right? This is behaviorally, this is similar to a thread pool with a size of 10. A maximum concurrency of 10, but using virtual threads that all go to the JVM's common fork join pool underneath, rather than managing local platform threads. Right, so that's where basically the story connects back to traditional threading, traditional thread management. All right, so all of these facilities, all of these options are available in Spring Framework 7.06, the latest at this point of time. It is effectively superseding the Spring Retry project for portfolio purposes. So within the Spring portfolio, say in Spring Integration, in Spring AMQP, in Spring Kafka, in various projects in the wider Spring ecosystem, you'll find, in the current generation, you'll find use of these facilities. They all reuse the core.retry features coming in Spring Framework 7, which actually was one of the design goals that I haven't mentioned before, was provide sufficient capabilities for the purposes in the entire Spring portfolio. Right, and the virtual thread support, sort of a related story, but obviously already a little bit longer coming and still continuing. Check it out, there's many things you can do. There's the virtual threads enable true flag in boot. There's many facilities at core Spring Framework level already since Spring Framework 6.1, being at least virtual threads oriented or virtual threads friendly, right? You can use all those facilities, simple async task executor, even the retry management, even the concurrency limiting. You can use all of this with regular platform threads. It's just not going to scale as much, right? You're going to block a platform thread, right? You get operating system level blocked threads through it. So some of those facilities, if they are trying to be virtual threads friendly, virtual threads oriented, it just means that what they do and how they are designed makes particular sense with virtual threads, where it's kind of natural and idiomatic to do what they do against the virtual threading architecture. All right. That is all I had for you so far. Bit of a pretty complete rundown of what we currently do here. If there are any questions, I'm happy to take them. I'm also going to look at the app, the Woo app, and the questions afterwards, right? If in case you have any that you are going to add there, I can also respond there. Right. So thanks for your attention. If there are any immediate questions, we have 2 minutes left. Sure.
For your, the virtual threads support, is there any built-in support for context propagation, like MDC or the trace IDs as well?
All right, good question. So the question is for the virtual thread arrangement, what about context propagation? A very common problem. The best you can currently do is to take our context propagating task decorator, which is part of the task executor world, and basically apply it to this, like literally the simple async task executor, set task decorator, specify this thing. And what it's going to do, it uses context propagation, as known from Micrometer. It basically takes a snapshot of the calling thread, all the context that the calling thread, the one that actually spawns the new thread, it takes a snapshot and passes it on to the new thread. So this new thread is going to see the same the same context, which is basically predefined thread locals, that the original thread saw. Makes a lot of sense for monitoring, makes a lot of sense for custom state as well. It's a necessary part of the picture. You can do this in a thread factory arrangement theoretically as well, but I recommend doing it through a task decorator. Any other immediate question? 15 seconds left. You'd have to be quick. Otherwise, well, sure. So transactions in combination with retrying. So the question was, how does this interact, right? Is it going to create a new transaction? Theoretically, you can combine the interceptors in any way you want, but obviously there's a regular way of doing this. Transactions are part of the target operation, right? So in particular, if you think about, say, database interactions, they are often going to fail late when you try to commit, basically. Oops, locking failure, right? You're a deadlock loser. So there's many exceptions that are worth retrying, but they only happen as you try to commit the transaction. The target operation would usually be transactional. And if you retry, you basically retry the entire transaction. There's a new transaction for every retry attempt. That's the standard mode of operation. And that's also what I would strongly recommend to hold on to. Right. Well, thanks for your attention so far. Any questions, please use the Woover app and enjoy the rest of the show.